Okay, so in the last one, we talked about how there's this idea of a matrix being invertible. Sometimes a square matrix is invertible. In fact, most of the time it is. But there are some occasions when it's not invertible, and we would like to be able to tell the difference. So, what's an easy way of doing that? Well, there's this number that we can associate to a square matrix called the determinant of that square matrix. And that determinant will determine whether or not that matrix is invertible or not. This determinant is pretty tricky to compute. Lots of moving parts, lots of things to think about. So we'll spend some time here talking about it. But it's also very important for other contexts, even within this own class. So please make sure that you're feeling solid about the notion of the determinant because you're going to be computing these things. Okay. It's also important for your life, and there's like real deep stuff that we could say about this, but we're going to give it a nice intro level treatment. Okay. All right. So yeah, determinants. So for the purposes of today's discussion, we're going to assume A is an n by n square matrix. Oh, that's a little bit redundant because, of course, if the number of rows is the same as the number of columns, then it's a square matrix. Okay, and then we're going to define the determinant of A. This is going to be denoted like this. This is going to be the determinant of A. I haven't told you what it is yet, of course. Okay. And again, this is a calculation intensive number that we're going to squeeze out from the entries of A. Okay, so how does this work? So how to compute? The determinant of A. Well, so what we're going to do is, what I'll do is just describe with increasing complexity how to compute the determinant. Because for a 1 by 1 matrix, the determinant is real easy. In the 1 by 1 case, A is simply a matrix with one entry. And guess what the determinant is? It is simply that entry. Okay? So the determinant of the matrix that contains the number pi is pi. Cool. The 2 by 2 case is slightly more complicated, but still pretty friendly. In this case, A has 4 entries, A, B, which I'll call A, B, C, and D. The determinant of A, and you're just going to accept this, and we're going to take this almost like a definition. The determinant of A is going to be AD minus BC. Okay, it's the product of the diagonal entries minus the product of the off-diagonal entries. Remember, we refer to this as sometimes the main diagonal or the diagonal of the matrix. That is the places where the row index and the column index are the same, remember. This is the 1, 1 entry. This is the 2, 2 entry. And we call entries which are not on the main diagonal, we call those off-diagonal entries. These are off-diagonal entries, B and C. And again, the determinant of a 2 by 2 is the product of the diagonals minus the product of the off diagonals. Okay? This you should just remember. Okay? Just remember it. Okay? There are ways of justifying this in terms of stuff that we're going to be learning in just a little bit called cofactor expansion. But I recommend that you just remember this. It's not hard, and you'll use this often enough in your life that this will it'll pay off to just remember things. Okay? Let's talk about the 3 by 3 case, okay? And the 3 by 3 case is going to be pretty complicated. This is it ends up being a sum that involves 6 different terms. Each of those 6 different terms end up having 3 different factors in each one, and nightmare. So we would sure like a way of organizing this discussion in such a way that if we just remember a kind of method, not only is this method going to help us to compute the determinant of a 3 by 3 matrix, it will help us determine the determinant for an n by n matrix in principle. Okay. So let's talk about something called cofactor expansion. So let me make the following definition. Given a square matrix A, I'm going to define Mij. Okay, M sub ij, and this is the matrix, and we'll assume the n minus 1 by n minus 1. So it has one less row and one less column. It's going to be a square matrix of one sort of one notch smaller. The n minus 1 by n minus 1 matrix obtained from A by deleting the ith row and jth column. So let's take a look at an example here. So for example, suppose that we have the matrix A being the 3 by 3 matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. Then by M11, I mean the matrix that we obtain by deleting the first row. The first row, we take this one here on the left. That's going to be referred to the row index, the first row and the first column. And if I delete the first row and the first column, what I'm left with is this 2 by 2 matrix right here, 5, 6, 8, 9. And indeed, that's what M11 will be. What will M13 be? So first row again, we delete it, but now we delete the third column. And what we're left with is 4, 5, 7, 8. That is 4, 5 in the first row and 7, 8 in the third row. What about something like M21? Well, here we delete the second row because of the 2 here, and then the first column. And what we're left with is 2, 3, 8, 9. And what is M22? This would be deleting the second row and second column. And what we're left with, can you see it, is 1, 3, 7, 9. Make sure you understand this. 1, 3, 7, 9. Okay? So that's Mij. We are going to define the ij cofactor. The ij cofactor, the ij cofactor definition. The I comma j cofactor, this is the notion I'm defining here, is, and did I say this was computationally intensive? So don't freak out. It's going to look weird. It's going to be -1 to the I plus j times the determinant of Mij. So -1 to the I plus j. Remember, -1 to any power is either just +1 if I plus j in this case is even, and it's negative. Did I say that one right? +1 if I plus j is even, and it's -1 if I plus j is odd. Okay. So this thing here is just a sign gadget. It's either plus or minus 1. Okay. The determinant of Mij, please notice, this comes from A. Okay. And it's the determinant of a smaller square matrix. Okay. And we're going to call this product here, we're going to call that the ij cofactor of A. Okay. Then, and here's a fact, which I'm going to shove down your throat. Fact. Oh, speaking of shoving down things down your throat, I just want to, because I feel like I should tell you. Well, have you heard of this? It's called foie gras, and it's a delicacy. It's a food. It's a thing that people eat. I don't eat it, but it's a thing that people eat. And the way that it's produced is a farmer will take a steel pipe and shove it down the throat of a goose, sometimes a duck, but let's just take a goose, okay? Um, Shove it down the throat of the goose, and then we'll force feed the goose delectable things like oats and nuts and figs, in order to and overfeed the goose so that its liver becomes engorged and fatty. Okay. Then, when the time is ripe, the farmer will take a blade, cut the throat of the goose, stab the goose, ripping open its carcass, carving out its liver, and then package it and then sell it to rich people. Yeah? This is considered animal abuse in the state of California. I at least this 2 years ago. I've been telling this story for years, and many of you have already heard it. But yeah, it's important for you to hear. Why am I talking about it right now? Well, it's because you're the goose, and I'm the farmer. Okay. And when I present a fact like this without justifying what I'm about to say, it's like I'm sticking a steel pipe down your throat and I'm force feeding you. And I'm not doing it to fatten up your liver. Fattening up your brain. And I'm not exactly selling your brain to rich people. I mean, I don't make money that way. I mean, come to think of it, you pay me in some way for the pleasure. Yeah, right? For and you know why I do all of this, right? It's because of the money. It's because it enriches me, the filthy lucre of it all. Yeah. Okay. So anyway, keep that in mind. How does that make you feel? See, the funny thing is that many students tell me I kind of like it. So you ask yourself. You have to make that decision for yourself. Here's the fact. If you want to compute the determinant of an n by n matrix, it can be obtained by computing the sum from, I'll just say the sum of the ij cofactor. So negative 1, maybe I'll write it like this. Negative 1 to the I plus j times aij times the determinant of mij. So aij, just to be clear, this thing here is the ij entry of the matrix. And the rest of it, this part here together with that part there, that's the ij cofactor that I was talking about up here. Okay? And we can do this kind of expansion. We can write this formula down where we take the entries along any row or any column. We call this cofactor expansion along a row or a column. Okay? We call this cofactor expansion along the row or column. Okay? So let me show you with an example. And actually, I can probably justify, in terms of this thing that we just learned, this fact right here. So let's take a look. So for example, suppose A is this matrix A, B, C, D, the 2 by 2. Then what this cofactor expansion, let's do cofactor expansion along row 1. What this gives us is -1 to the 1 plus 1. Okay, so I'm taking my first entry here to be the 1 1 entry. Because it's the 1 1 entry, I have I plus j being 1 plus 1. I'm going to take a11, which is a, times the determinant of the matrix that I obtained by deleting the first row and the first row in the first column. But that's the 1 by 1 matrix, D. Okay. This looks really dumb, but I'm just showing you, okay, how this thing works. Then I'm going to add to this because I'm taking a sum. See, look, it's a sum. Okay? I'm adding to this and I'm cofactor expanding along row 1. So now I'm going to look at the 1 2 entry. Here's the 1 2 entry. So I have -1 to the 1 plus 2 times the 1 2 entry, which is B, times the determinant of the matrix I obtained by deleting the first row and second column. That's C. And this is just an extraordinarily fancy way of writing. And this is supposed to be the determinant of A, by the way. Let me do this better. This is the determinant of A is equal to all this. This just ends up being, because -1 to the 1 plus 1 is 1, A times the determinant of D. The determinant of 1 by 1 is just the entry in that 1 by 1. So this is AD minus, oh wait, how do I know it's minus? Because it's -1 to the 1 plus 2. 1 plus 2 is odd. -1 to the odd is -1 plus BC, or minus BC. And we get the same, thing that we got up here. All right. So if you're cynical and saying, this guy is just farming us for money right now, what is he being truthful when he tells us these things? Like, maybe he's just lying to us and making things up as he goes along. Well, I am kind of making things up as I go along, but at least you see the consistency between claims I made earlier, like that the determinant of A is AD minus BC, and that cofactor expansion works, okay? Because in the 2 by 2 case, you get the same answer, the same formula for the determinant of a 2 by 2, okay? How does this work for a 3 by 3? So I'm not gonna do this with ABCs and all that. I'm gonna do a fixed set of numbers here. So let's say that I was to do 1, -2, 0, 7, 8. Oh my God, why did I do that? Those are big numbers. And then 1, 3, and 0. Okay. Well, I could do cofactor expansion along row 1, just like I did before. And I'm going to do this once. Okay. I'm going to do cofactor expansion along row 1. So I'm going to go think about cofactor expanding along here. Starting with the 1 1 entry, what we get is, so the determinant of A, maybe I'll do it down here. Determinant of A is going to be -1 to the 1 plus 1 times A sub 1 1, which is 1. You all see that? You can't talk. Times the determinant of the 2 by 2 matrix that I get by deleting the first row and the first column. So that's going to be the determinant of 8, 1, 3, 0. That's my first term in my determinant. I'm going to have 2 more. And you're puking in your mouth, but it's okay. As long as you're not puking up the really expensive figs and dates that I've been force feeding you. Sorry. -1 to the 1 plus 2 is the next entry. Row 1, column 2. Then I take the entry in the 1, 2 position. That's this entry. And then I multiply by the determinant of the 2 by 2 that I obtained by deleting the first row and second column. That's 7, 8. No, I'm sorry, 7, 1, 1, 0. And one more term to go, which is negative 1 to the 1 plus 3 times a sub 1, 3. That's 0, though. Oh, my goodness. That 0 feels so good. It feels so good because we know that this term is going to die. But just for completeness, this is the determinant of 7, 8, 1, 3. Can you all follow that? And now we have to do the hardest part of the problem, which is the arithmetic. This ends up being, so I'm going to look here. Look here. That's positive 1, because 1 plus 1 is even, times 1, so that's 1, times the determinant of this, which is 0 minus 3. So I think I get negative 3 for the first term. Okay? How about the second one? Well, I have negative 1 to the third power, which is negative 1, times negative 2, which is 2, times the determinant of this, which I believe is 1. No, negative 1. It's a lot of negative signs in a row, buddy. So I think that ends up being, though... Oh, no, it's so many negative signs. 1. I think it ends up being negative 2. God, I hope that's right. And then finally, we have positive 1 times 0. Whatever. This is negative 5. Okay? I think. But we can solve the problem in another way. And here's what I want to say. We can cofactor expand along any row or any column. So I'm going to choose to cofactor expand along column 3. Why? Because there are gobs and gobs of zeros in row 3, and you see how lovely it is when your entries are 0, because it kills the entire term. So let's do cofactor expansion on the same matrix, but now along column 3. And this will be the last calculation I do. In which case we get that the determinant of A is equal to... Okay, now, see, I'm just not even going to write anything down, because I'm starting here in column 3. That's... I mean, it doesn't matter what's happening there, because I know I'm going to multiply the subsequent term by 0. Yeah? So nothing matters. It could be anything, and I'm going to multiply by 0. It doesn't matter. What does matter is, of course, the next entry. Here, I have to think about that one. Now, first of all, what's the row index? That's 2. And what's the column index? That's 5. So this is going to be negative 1. Wait, the column index is 3, I mean. And 2 plus 3 is 5. My brain is rotting. Okay. Negative 1 to the 2 plus 3 times the 2, 3 entry, which is 1, times the determinant of the 2 by 2 matrix that I get by deleting the second column and the second row and third column. Do you see that matrix there? It's 1, negative 2, and then 1, 3. 1, negative 2, 1, 3. Now we do the arithmetic. Oh, sorry, I'm not quite done, because I have to continue my cofactor expansion to the last entry of the third column. But notice that that's 0 again, okay? So this is really all we have to do. This calculation is done. Well, as soon as we do the arithmetic, which is the hardest part. Hey, what's negative 1 to the 2 plus 3? You can't say anything, but it's negative 1 because 2 plus 3 is odd, because it's 5. So we have negative 1 times 1. Times 1 times the determinant of 1 negative. What's the determinant? It's the product of the diagonals minus the product of the off diagonals. So that feels like to me 3 minus negative 2. Yeah. And I think if I did this right, it's negative 5. And oh my god, it's the same thing. Okay. I'm pretty sure this thing here is negative 5. Now, why on earth do we care about the determinant? Well, I'll say something about that for maybe 5 minutes in the next video. But this video is really about computing determinants. And in principle, if you know how to do cofactor expansion, you can do the determinant of, in principle, any n by n matrix. Okay? So that's good stuff. All right. See you in the next one.